Hello, everyone. Welcome to the third section of System of Linear Equations, the one that I like to call preliminaries, because the ultimate goal of this chapter is to use a Gauss-Jordan elimination algorithm to find the general solution of a system of linear equation. But I need some little technical definition on matrices. That section could have been in chapter one where we talked about matrices, but it could have felt a bit out of place. But it is something that we define on matrices. So we're not really thinking about system right now. These definitions are really for matrices in general. The first definition is the notion of leading coefficient or the leading coefficients of a matrix. So for every single row, you can find the leading coefficient of that row by finding the first non-zero entry from the left. So if your row is full of zeros, then there's no leading coefficient. But if from the left, you find an entry that is non-zero, the first one, that's called your leading coefficient. So let's just do some example very, very quickly. Let's circle together the leading coefficients of the following matrices. So for the first one, let's go. So I'm trying to find the first non-zero entry. So that's -1 here. So -1 is my first leading coefficient on my first row. On the second row, we have all zeros, so there's no leading coefficient. On the third row, right in the first column, we have a leading coefficient. And then you don't move further. There's only one leading coefficient, the first one that you find. And then for the last one here, we have 3 is the first non-zero entry from the left in the fifth column. So in the first row, we have -1. In the second row, we have nothing. In the third row, we have 2. And in the last fourth row, we have 3. So same thing for the second example here. But you can see here the first row, it's filled with zeros. Same thing for the second and third row. So there's no leading coefficient. But then for the last row, the fourth row, we have a non-zero entry in the second column. So that's my only leading coefficient for that matrix. So 2 in the last row. Once you know where your leading coefficients are, we can talk about special forms for matrices. The first one is echelon form. What is a matrix in echelon form or row echelon form? Well, a matrix is in echelon form if it satisfies two specific conditions. The first one, if your matrix has any row of zeros, they need to be at the bottom of your matrix. Or another way to say it is that all the rows with non-zero elements are above the zero rows. So that's very important. If you have rows of zeros, they are at the bottom. If there's no rows of zeros, then automatically this first condition is satisfied. The one that is a bit trickier, where you need to think about it, is the second thing is, where are the leading coefficients? So the trick here is the following. So if you have a leading coefficient in a specific row, the next one will always be in the column to the right, not necessarily right after, but all those leading coefficients, they go from left to right. So you can have like a leading coefficient in column 1, then column 3 and column 5, but you cannot have two leading coefficients in the same column, or you cannot go back. So if you have a leading coefficient, let's say in column 2, and then in column 1, as you go down the rows, it doesn't work. So the leading coefficients, so the leading coefficient of a non-zero row is always strictly to the right, not necessarily right after of the leading coefficient of the row above it. So this is what I like also to call the staircase pattern. We will see that together in a moment. So when your matrix does satisfy the condition of being in echelon form, these coefficients, they have a special name. They're now pivots of your matrix. Pivot, for those who get the reference here. So when the matrix is in echelon form, those leading coefficients are pivots of the matrix. But if your matrix is not in echelon form, there's no pivots initially. And when you have a matrix in echelon form, So when these leading coefficients are pivots, if you simply count the number of circles in your echelon form matrix, we call this the rank of your matrix. So when the matrix is in echelon form, the number of pivots is the rank of your matrix. The last definition, I know I'm dumping a lot of information on you right now. This is classic me. I'm the worst. Is the notion of, and I love saying it, is the notion of row reduce echelon form. So for a matrix to be in a row reduce echelon form, it needs to be, of course, in echelon form, but there's two more conditions to check. The third condition is that every pivot needs to be equal to 1. So all the pivots are 1. If one of the pivots is -1 or 5, 0, 0.5, or etc., it doesn't work. So that's fairly easy to see that this third condition needs for all pivots to be 1. And then the last one, also not too difficult to check, but it needs to be true also, is that every pivot is the only non-zero entry in its respective column. So if you have a pivot in column, let's say 5, it needs to be 1, and everything above it and everything below it needs to be 0. So it's the only non-zero entry of its own column. But you only check in the column where the pivot is. Anyways, the best way to digest all that information, because it's not too difficult, is to look at a bunch of examples. Let's look at some examples. So for every matrix, we're going to check if the matrix is in echelon form. So when I'm going to write EF only, is for echelon form, but not row reduce echelon form, because obviously row reduce echelon form is in echelon form. If I write row reduce echelon form, then that's the most restrictive form of echelon form. And if it's not in echelon form, I will just write neither or not or whatever. And then when it is in echelon form or in row reduce echelon form, we're going to be computing. It's not computation at all here, but we're going to be finding the rank of our matrix. So here we go. First example here, A. Let's find our leading coefficients. So we have 2, -4, and 1. Remember, I start from the left. I find the first non-zero entry. And now that my leading coefficients are circled, let's check all the conditions. So we don't have any row of zeros, so the first condition is met, so we don't have to worry about that. Is this matrix in echelon form? Are the pivots going from left to right? And the answer is yes here, because we have a pivot in the first column, and then the second one is in the second column, and then the third one is in the fifth column. So we are going from left to right. So some people sometimes likes to draw that little stairway pattern. So here, when I'm like looking at my structure, these steps of the stairways that is upside down only goes up by 1. I'm not sure if it helps here, but this matrix is in echelon form. So that matrix is in echelon form. Is it in a row reduce echelon form? No, some of those pivots are not equal to 1. But anyways, because it is in echelon form, we can find the rank. And because there's 3 circles here, the rank is 3. Next example. So let's find our leading coefficient. So in the first row, we have 2. Our second row is filled with 0, so we have none. And then our last row is, for the last row, the third row, we have a -4. Is this matrix in echelon form? The answer is no. And the reason why it's not in echelon form, we have a row of 0, and that row of zeros is not at the bottom of the matrix. So this matrix is not in echelon form. So this is not in echelon form. So that's it for that one. But it's almost in echelon form. If you could simply swap those two rows, we would have something in echelon form. And this is something that we're going to do very soon. Next example, the 0 matrix. Is the 0 matrix in echelon form or row reduced in echelon form? The answer is actually yes for both, because here all the rows of the zeros are at the bottom. So there's no leading coefficient here. All the rows of zeros are at the bottom. And so the first condition is satisfied. The second condition is if you have any leading coefficients, they need to go from left to right. And because we don't have any leading coefficients, it does not contradict that second point. So that matrix is actually in echelon form. Is it in row reduced echelon form? And strangely, yes, it is, because if I add any pivots, they would need to be equal to 1. And because I don't have any, they are satisfying that condition. And then the fourth condition is to check that if you have any pivots, they need to be alone in their column. Because there's none, you're not contradicting that point. So this matrix is actually in a row reduced echelon form, and the rank of that matrix is 0. And actually, the only matrix or the only matrices where the rank is 0 are the 0 matrices. So this is like, for example, if I use a notation from the previous chapter, this is a 0, 3 by 4. This matrix is in row reduced echelon form, and the rank is 0. And the only matrices of rank 0s are the 0 matrices, because if not, you have a leading coefficient. Either you're not in echelon form or your rank is at least 1. Next up, here we go. So on the first row here, we have 1. On the second row, we have 1. And the third row is filled with zeros. So is this matrix in echelon form? So we have a row of 0, and it's at the bottom. So good. We have 2 leading coefficient in column 2 first for the first one, and then in column 3. So you go from 2 to 3. So from left to right, this is in echelon form. Are you in row reduced echelon form? Our 2 pivots here are both 1, so the third condition is satisfied. But as you can see here in the third column, that one is not alone because there's a 2 on top of it. So this matrix is not in a row reduced echelon form. By the way, the first pivot is alone. That's the only non-zero entry in its column, but it's the second pivot that is not alone. So this is just in echelon form. We can still talk about rank here. So there's 2 pivots, so the rank is 2. What about the last example? And you can see where this goes. We still have those 2 pivots in the same spot. We still have that row of zeros at the bottom. So using the same arguments, we see that this is in echelon form. Is this in row reduced echelon form? Well, all pivots are equal to 1, just like the previous example. And now when you look at their columns and their respective columns, for the first pivot and the second one, they're both alone in their respective column. The first one here, so the first pivot in the second column is 1, and it's alone in column 1. And the second pivot here in column 3 is also alone. So this matrix is in row, oh my God, row reduced echelon form, and the rank is again 2. So just be careful. Right now, it's just being able to find where the leading coefficients are and to check if they follow a specific structure. So for echelon form, every row of zeros needs to be at the bottom, if any, and then those pivots needs to go from left to right. When I say left to right, I'm talking about their column position. So when you list the column numbers, they need to be increasing, and then to be in row reduced echelon form, 2 extra things to check. Those pivots needs to be 1, and those pivots needs to be alone in their respective columns. That's super important. So for this small section about finding if a matrix is in echelon form or in a row reduced echelon form, and to be able to find the rank or to compute the rank, that's it. That's all. Bye-bye.